Welcome back. This is Jonathan Gardner covering Sergey Lang's Basic Mathematics. This is chapter 6, for section 5, Characterization of Isometries. So in this section, we're going to try to list all the possible isometries, and we're going to do it with 3 more theorems, I think, 4, 5, and 6, yes, that build on the same pattern we used for Theorem 3. So let's remind ourselves what Theorem 3 from this chapter looks like. So Theorem 3 basically says if you have a isometry with 3 fixed points that are not linear, then F must be the identity, right? That's Theorem 3. Not going through the proof here at this time. You can go back and review a couple sections ago when we did go through the proof. Right now we're going to prove Theorem 4. Theorem 4 says we have F as an isometry and with 2 fixed points, okay? And so we're going to see what kind of isometries can satisfy this. Okay? And the theorem is going to say that either F is the identity or F is a reflection through the line. The 2 fixed points are going to be called P and Q are the 2 fixed points. So the line passing through PQ. Okay? So let's go ahead and let's get to that proof. So first thing we're going to do is we're going to note that, recall that an isometry means that distance is preserved. And so I'm going to draw this little picture here. Let's use orange, why not? And this picture is also found in your book. So we're going to draw a line here. And this is going to be the point P and the point Q. Okay? So when the isometry is applied, F is applied, F of P equals P and F of Q equals Q. Let's write that down. I'll use a blue for the proof here. F of P is P and F of Q is Q. That's what it means to be a fixed point. So what about another point, let's say M, and we're going to, for convenience sake, draw a perpendicular bisector. Green, why not? Okay. And I'm going to draw it 20 units up this way and 20 units down that way. So there's a perpendicular bisector, and I'm just going to say that this is perpendicular even though I didn't measure it very precisely. And at one end I'm going to put the point M. So this is M. Okay. Note that the distance from P to M and P to Q is the same, and this is from Pythagoras' theorem. This is the corollary from Pythagoras' theorem that we proved quite a while ago. Pythagoras' theorem is a theorem, it's not an assumption. You can't prove it. So those 2 lines right there, those 2 blue lines are the same length. Okay? Now at this point in the proof, we have to make a decision about what F of M is going to equal. Right? If F of M is fixed, then we have Theorem 3. So F is I. Okay? So that's one possible branch. Okay, so if F of M is not equal to M, well, the distance from P to M and the distance to Q to M are all the same, right, because of Pythagoras' theorem. This is a perpendicular bisector after all. And that means that the distance from P to M prime has to be the same as the distance from P to M because it's distance preserving, and the same for the distance from Q to M prime, wherever M prime is. So F of M is M prime. I forgot to mention that. Okay, so where could M prime lie? The only answer is M prime has to lie over here. Let's draw that in green. So M prime must be this point down here, okay, on the other end of the perpendicular bisector, so that these 2 lines are the same. PM prime, the same as PM. I should probably take the caps off before I try to draw the line. And QM prime is the same as QM. We have, in fact, drawn a rhombus. So all these distances are the same. Because it's an isometry, distance is preserved. So what possible isometries can be described by this mapping? Let O be the point of intersection. That's O right there. Okay? The midpoint between P and Q. And so we also know that the distance from O to M is also preserved, and hence the reflection of the line through M is a reflection because it's crossing O, so M has to go there. So all of these points along here have to be preserved. All of these points along here have to maintain their distance. So this is 100% F is a reflection through the line. Through the line PQ. All right, this isn't quite enough. I mean, we've proven that this is a possible isometry, but perhaps in the universe there is another isometry that we missed. So how can we prove that it is the only possible isometry? This is the trick that we're going to use. Suppose that we have, so we're going to say that R is a reflection through the line PQ. Okay, and we're going to say R of M equals M prime. That's the point on the other side of the line, right? That's what the reflections do. And on the other hand, we have R of M prime is equal to M, noting that R is its own inverse. Okay. So suppose that we had another isometry so we have R composed with some other isometry. Okay. This also leaves PQ fixed. So R composed with F leaves PQ fixed. Okay, so this is another possible solution. Okay. Furthermore, we know that R applied to F of M has to equal R of M prime, because we said that F applied to M gives M prime. Okay, and that will just give you M back. Okay, hence R applied to F also leaves M fixed. So what is R to the F? Well, that must mean, because of Theorem 3 says it is I. So R to F leaves M fixed, PQ fixed, and it leaves M fixed, therefore R of F must be I. Okay, so R applied to R applied to F is the same as R applied to I. Therefore F must be equal to I. R, I'm sorry. So this we know is the identity right here. That's a very poor done thing there. So we have I applied to F, R applied to I, therefore F must be equal to R. So F and R must be the same. There is no other option for what the solution for the second case is. So we've just proved with Theorem 4 that if we have two fixed points, then either the function, the mapping must be the identity, or the mapping must be a reflection through the line PQ. There's no other options. Okay. You might take some time to think about this and review it until you understand how this proof works and why it works. The key point here is I just picked this arbitrarily. Okay, and I noted before I picked this what RF would be. All right, let's move on. Let's do Theorem 4 now. Theorem 5. I'm sorry, Theorem 5. Theorem 5 says, so Theorem 3 was all about 3 fixed points. Theorem 4 was about 2 fixed points. So we have F is an isometry with 1 fixed point. 1 fixed point, O. Okay, so, and then the theorem says that either F is I, okay, or F is a rotation, around O, or F is a reflection through rotation around O composed with a reflection of a line through O. These are the 3 possible options. Okay, so let's do the proof for this one. Okay, the proof. So let's let P be any point not equal to O, any point at all. Okay, if F of P is equal to P, then P is fixed, and that leads us to Theorem 4, I'm sorry. 2 fixed points, right? And what does Theorem 4 say? That means F is I, or F is a reflection through the line PO. Okay, if F of P does not equal P, then the distance has to be preserved. So the distance from O to P must be equal, so let's say f of p is p prime, then the distance from O to P must be the distance to OP prime, right? And so what we end up with is a picture like this. I won't use rulers. So we have O, we have P, and we have P prime. And then this distance here is the same. And you should readily be able to see that this is an arc, and this looks a lot like a rotation, okay? Now we say there exists a rotation. We'll call it G, and it's P prime, right? But we'll just call that G, right? We're not talking about any other point, so we're going to say G, okay? Note that G inverse applied to P prime is equal to P. So the image of P prime, the inverse image of P prime, the inverse image of P prime through G is P, okay? Let us denote this rotation by G. It's a rotation. Therefore, if we had another, if F could be something else, then G inverse of F applied to P would be G inverse applied to P prime, I'm sorry, F would go to P prime, that's right, and that is going to give you P, okay? So this means G1 of F leaves P fixed. And so according to Theorem 4, that says G inverse applied to F must be the identity or reflection through the line PO, okay? Is a reflection R. In the first case we have, so if it's the identity, so if G inverse composed with F is the identity, okay, then we do the trick that we did before. So we say G composed with G prime, G inverse composed with F is the same as G composed with I, which is going to be G. So F, if we do this side first, then we get I composed with F must be equal to F. Therefore, we find F and G are one and the same. So F and G are the same rotation. Okay. In the second case, if G inverse composed with F is a reflection through the line PO, then we find G composed with G inverse composed with F is going to be the same as G composed with that reflection. So this is going to be called R, the reflection, G composed with R. But we also note that this is the identity, so F is equal to G composed with R. And so F is some rotation possibly composed with a reflection. Okay? So F could be just a rotation, or F could be a rotation applied with some R, or, going back to here, F could be the identity, or F could be the reflection. So let's list that out. F could be the identity, check. F could be a rotation around O, so that would be down here, check. F could be rotation composed with a reflection, check. F could also be just a reflection with rotation with 0 degrees and a reflection. So there's another case that I forgot to mention. Anyway, whatever. So we have now, with one fixed point, a proof of all the possibilities that F could be. Okay, F could be a rotation, it could be a rotation composed with a reflection, it could be the identity, it could be the reflection. Okay, all right, continuing on. Notice that it relies upon the inverses to get these proofs. So inverse is really useful from solving these kind of things. Now let's go for Theorem 6. Theorem 6 is the granddaddy of all of these guys. Okay, so F is an isometry. Okay, that's all we're assuming. Okay, if F has no fixed points, okay, then F is a translation, or it could be a translation composed, or the composite of a translation and a rotation, or F could be the composite of a translation, a rotation, and a reflection through a line. Okay, or the composite transfer reflection through a line, any combination of these guys. Okay, of course F could also be the identity. Okay, so one of these possibilities, but this basically describes the complete set of all possible isometries that F could be. Let's go through this proof, and this proof is not unlike the proof that we've done before. Okay, so we're going to say if F has 0 fixed points, no fixed points, okay? So let O be any point, and let P equals F applied to O, okay? Let T be a translation such that TO equals P. So this is a T is just TOP. So such that T of O gives you P. That's a translation T. Then T to the minus 1 is also a translation, and T to the minus 1 of P will give you O, right? Hence, T to the minus 1 applied to F applied to O is the same as T to the minus 1 applied to P, which is O. So T to the minus 1 composed with F leaves O fixed. Do you see how that works? So we started with just assuming that there is a translation, and this translation composed with F will leave O fixed. So whatever F is, it has to leave O fixed. All right. We can therefore apply Theorem 5. So Theorem 5 says that T composed with F, T inverse composed with F, could be a rotation around G, or it could be a rotation composed with a reflection, or it could be identity, etc., etc. Okay, we're not going to go there. That's pretty easy to show. So let's suppose that T inverse composed with F is the rotation around O. Okay. Then we say F must be T composed with G. Okay. If we suppose that T inverse composed with F is a rotation, a reflection composed with a rotation, then we say F must be T composed with G composed with R. How do we get there from there? Well, we just take T composed with T to the inverse composed with F. I'm sorry, F is the same as T composed with G. And so the inverse, this is the identity, this is F. F must be T of G. Same thing over here. We take T composed with T inverse composed with F. It's the same as T composed with G composed with R. So we get F is equal to T, G, R. Sorry, my handwriting is so poor here. Notice that what we're doing here, this pattern, that's the same as if you have 1/2 x is equal to 5 or whatever like that. And we've gotten into the habit of saying, well, this is just the same as x equals 2 times 5, right? But we've forgotten why we're doing that. That's because we're multiplying 2 by 1/2 by x, the same as 2 by 5. So we get x is equal to 10, right? X equals 2.5. And so all we're doing is we're multiplying both sides, or composing both sides, by the t, okay? So we have F as T of G, we have F as T of G of R, and of course we can do trivial proofs to prove the other possibilities as well. Now, the first exercise of this section is to prove that every isometry has an inverse, okay? All you have to do is to prove that T, G, and R all have inverses. And if you can do that, then you can find an inverse for every single possible isometry. The other problems are also similar. They're not too difficult, involve some drawings, and shouldn't be too hard. Next section, we will finally cover congruence. Guys, thanks for your time. Take care, and bye-bye. Hey guys, thanks for watching this video. This video is part of my series on Sergey Lang's Basic Mathematics. You can click here to watch the rest of the videos in the playlist. You can click here to learn more about me, and you can click here to support my channel. Thank you so much. Bye-bye.